Hello, everybody. Welcome to Decode 2020. My name is Andy Liu. I am a shellcode expert developer at Trend Micro Research. Today, I'll show you how I develop a shellcode expert for my UseAfterFree vulnerability. In this presentation, I'll show you the roadmap and explain the ideas and the concepts. I also share my personal experience. It's a very complicated topic. It requires some deep understanding of the computer memory layout. So I'll try to explain everything clearly and try to make everything simple. Okay, so as we know it, UseAfterFree bugs are very common. It happens everywhere. Basically, when we are programming, we will create some objects in the memory and use some pointer to access the objects. After we have done with the objects, we will delete them, and the system could reclaim the memory and reuse them. In some cases, the object may have been deleted, but we just don't know it. And we may still try to access the object with a dangle pointer. In this case, the data in the object has been changed. So the program may crash or it may not. It really depends on what data is in the object. Okay, so in this situation, it's really hard to find this kind of bug. It's really bad for the programmers. But for me, I'll try to make use of this situation and try to control the data in the object and make it to jump to my shellcode. Like this kind of UseAfterFree vulnerabilities, most of the exploit will happen in browser and the JavaScript. Since everybody is using web browser, if we can entice a user to open a web page we controlled, and if the user's web browser is vulnerable to a vulnerability, very likely we can control his computer. We like JavaScript since like it's a programming language, and with a programming language, it's easy for us to control the memory layout and make our exploit work. So to exploit this kind of vulnerabilities, we use two major techniques. The first one is heap spraying. We'll use heap spraying to inject our shellcode into the memory. And the second one is type confusion. We use type confusion to rewrite the EIP and make the program jump to our shellcode. And from there, we take control of the computer. Okay, first let's check the object. For any object, very likely, in most cases, the first 4 bytes will be a pointer, which point to a virtual function table. And when we make a function call on this object, the system will check this function table and find the right function and make a function call on it. So here's some sample code on the function call. You can see ESI will point to the object, and the EAS will be the virtual function table. And with the offset, the system will fetch the address of the function and make a function call on it. And in this case, since the object has been freed, and this memory, if we can let the C team to reassign this memory to under our control, we can put some data in it and make a function call on the old pointer. And very likely, the program code will jump to our controlled address. And from there, we can control everything. So for this to happen, it's very important that we know the object size. We know the size of the freed memory. If we can find a new type of object with exactly the same size, and we will create a new object, and very likely the C team will reuse the memory with our new object so that we can control the data. So it seems string is a very good choice, since like we can control the contents and then we can control the size of the string. But actually, string are allocated in a different heap, and it will never reuse the same memory as the objects. So we still need to find a new type of object with the same library, the same size. It's not easy every time. There is a library called heap function, which can help us to manage the heap layout and make it easier to reuse the same memory. But the code is very complicated, and for me, I don't like to use it, because the idea is very simple. I can write my own code, and everything is under my control. Okay, so let's talk about the heap spring. So the idea is to fill the heap with lots of long strings. And in each string, there will be our shellcode and some sled codes and then the virtual table. There's one thing to notice: that strings cannot be identical. If it's identical, the WindowsExec team will use a single one string for all of the strings. In that case, we cannot occupy a lot of heap memory. So our intention to put our shellcode to a fixed address like 0C0C0C or some other address, so that we can control we can set the EIP to this address, and the code will jump to her. So we will use an offset to move the shellcode inside the string, to move it forward or backward until it's at the address we want it to be. Okay, here is the heap spring code I used. You can see for each string, I use the index I use index as a content, so to make sure every string is different. And I use this offset to move the shellcode backward or forward inside the string, and to align it at the fixed address, like 0C0C0C. And we can change the string size and the loop counter each time, and to make sure like the memory is make sure the memory layout is like we want it. So here is the memory layout after a successful heap spring. We can see this memory block is filled with our strings. And in each string, there's our shellcode, and like we put the URC at the landing place, and it's the address we are gonna set to EIP. So inside the string, we need to move the shellcode backward or forward until it's sitting exactly at the landing place. Once it's done, we can set the EIP to this address and make a function call on the feed object, and it's very likely it's gonna change the code flow to our shellcode. It's simply easy, right? But on Windows, there's DEP, data execution prevention. With the DEP, the heaps are not actionable anymore. So anything in heap, we cannot activate it from there. Only code in code segment can be executed. So like it effectively stopped our shellcode from execution. Once the code jumps to our shellcode, the program will crash. Okay, so what we can do with it? So here comes return-oriented programming. Okay, since only code in code segment can be activated, we'll let the code will set our EIP to an address inside the code segment, and once it jump there, we're gonna run a small piece of our code and return, and we let it return to another small piece of our code inside the code segmentation, and so on. If we can chain these gadgets together and make it carefully, we can achieve some goal. We can make something happen, like we can call system function and change the heap and mark the heap as actionable, and so that we can run our shellcode. Okay, to make this happen, we need to control the stack. We need to put the address our RLP gadgets inside the stack. Okay, so it's impossible to control the stack, to change the data inside the stack. So what we can do? Okay, so we put our RLP gadgets inside in a heap memory, and we use a stack Pyrotence technique to set the EIP to our heap. The code is very simple. We just change EAX with EIP and return. The stack will go to our heap. Since we can see it in the sample code, every time we make a function call on the object, the EAX will point to the virtual function table. And in this case, we control the virtual function table. We control the content of the object. So we can set EAX point to our controlled heap. And once we exchange EAX with EIP, the stack will go to our controlled heap. And from there, with the RP gadgets, we make a 16 function call and change the heap to executable and run our shellcode. Okay, so here's some function calls we can make. The first one is virtual protect or virtual alloc. So this function will change the flag on the heap on the memory address we set and change the flag to the value we want to be. So carefully manage the stack layout and set these parameters, set the address as our shellcode address, and set the size to the right side, and set this flag, this protect flag as executable. Also, after calling this function, our shellcode will be executable. The second function call we can use is this function WindowsExec. So this function basically it will call a string. It will run a command string as a shell. So it's simpler compared to virtual protect. We just need to feed with a command string, and we convert this UseAfterFree vulnerability to a command injection. And since we control the object content, we can write our long command string there. Here, one thing to notice, the first parameter will be a pointer to the object itself. So we have to put the command string inside the object. And remember, the first 4 bytes will be a pointer to the virtual function table. So we cannot ruin it. We have to keep it valid. So we can use this value 28, 28, 28. It's a valid address, and its meaning is inside the command string. So with this method, we don't need to write a shellcode in the heap. We just provide a command string, and inside the shell command, we inject our shellcode there. Okay, the third method is call ntcontinue. This function is even powerful. With a single function call, it will set the EIP and change the stack pointer and enable the page executable with red flag on the heap on the memory address. So it's a very powerful function call. So for this function call, the first parameter is a pointer to a structure of thread context. It will start a new thread. So we check this context structure. Remember, the first 4 bytes or 8 bytes will still be a pointer to the virtual function table. So it had to be a valid address. But fortunately, this function call don't care about the first. It don't use the first parameter, so we can put anything there. There will be no conflicts. Okay, so with this function call, we start a new thread, and that thread will run our shellcode, and everything will be under our control. Okay, so for the ROP gadgets, we have a tool called manner.py to help us search all of the gadgets inside the code segment. It's an open source. It's an open source in Python, and it runs on immutable debugger and a Win debugger. But it only supports on Windows 32-bit platform. It's a very helpful tool. You can check it out from Google. Okay, so after DEP, there's still something we have to deal with. It's ASIL. With ASIL, the modules are loaded into random addresses every time. You know, in ROP, we need address of each gadget, and the address need to be fixed. But with ASIL, since the modules are loaded into different address every time, so we have to find out the gadget on the fly. It's significantly harder. So in this case, first there's still some old modules which don't support ASIL. So we can make use of that, like MSR VCR 71.dll. It's very widely used. But right now, it's very hard to find such kind of old modules. Most are I can see all of the modules are ASIL enabled right now. So we have to have another way to deal with it. So basically, we'll need an information leak vulnerability. So we can find the address of the module and find all of the gadgets we need on the fly and put them together, put them in a stack, and make a stack purity and jump to our shellcode. It's very hard. So how can we do from an information leak to ROP? So we'll need an arbitrary read primitive, so we can read anywhere in the memory. With any address, we can read the content. We will need this kind of ability. From there, we will need an address. We will read the address of an object. And from the object address, we can read the feature function table, and we can read one of the address for the functions. Since the function address will always be inside the code segment. So from there, we can get the address of the module, and we can calculate the module base address, and we can analyze the module and read its import table and find other modules. And we can also, from the export function table, find the function address like we want to use, like the virtual protect or the anti-continue. And we can also search the gadgets inside the code segment, like the stack purity gadgets. Okay, so once we have information leak vulnerability to help us to read the memory and find the correct gadgets and put everything together and make a function call and jump to our shellcode. We can get everything control and control the target computer. So I'll study CVE 2020-0674 as an example. It's Microsoft the IE script engine UseAfterFree vulnerability. I'll do it on Windows and with IE 11 with 64 bits. So to debug it, I used the x64 DBG. It's an open source debugger, and it's very similar to Ollie debug. For some people who like Ollie debug, it's very similar and it's very helpful. So in this case, the deleted object is it's a long array. It's a size of 100 array, and each element inside it is a variable, and the size of the variable is 24 bytes under 64-bit system. So we can calculate the size of the feed memory block as this size. And after the object has been deleted, we got 100 dangling pointers to use. So we'll reuse the memory with the property name object. You can see on the right, this is the structure of the new type of object. And we can control the size with the length of the name. The name is a string. And we can set the content with different of strings. And the size will be the length of the string multiplied to 2 and plus some control bytes. And we'll use 2 consecutive property names to reuse the freed memory. This way, we can leak the address of the second object. So this is the memory layout after we use the memory. We can see the dangler pointer is still, the system is still taking on at the variables, and the data have been changed under our control. We can set each type of the dangler pointer as anything we want. If we set the last one as 0.5, it means it's a double float. And if we read out the value, it's actually the address of the next object. And this way, we leak out the object address. And if we set the type as a string, and because the string address is controlled by us, we can use the dangler pointer to read anything from anywhere. So put them together. We read anywhere from the memory, and we'll read an object address, and from the object address, we read the virtual function table, and eventually to the module base address, and from the module, we'll find out the function we want to call, the system function like an NT-continue. And then finally, we'll fix a virtual function table and then make a function call on it. And from there, we jump to NT-continue with our control parameters. And finally, we got our shellcode executed, and it's done. For this UseAfterFree vulnerability, there have been a popular exploit by Methodwi. You can Google it and check into it if you like. So this is everything I want to say. Thank you, everybody. If you have any questions, you can drop an email to me at trentmichael.com. You can see it here. I will be glad to hear from you. Okay, thank you, everybody. Bye.